All right. So we will resume here and let's look. Let's do an example where we simulate some data and then we will try to do statistical inference on our simulated data. Okay. So, so here I'm going to just this is just for simulating the data. Okay, this is not part of our inference. So I'm going to just say in the simulated data, our true omega value is going to be 0.25. We're going to have 300 for our k. The number of players is going to be 8. Okay, and so using kind of the formulas, we'll get a true value for alpha and a true value for beta. I don't actually know what that's going to be. 0.25 times basically 300, so around 75 off by a tiny fraction, and around 225 off by a tiny fraction. Okay. And then so from there, I'm going to generate 8 random values from this beta distribution. Okay. So some of the players will have higher theta values. Some players will have lower theta values. Okay. They will be centered around, around approximately 0.25, but I've got 8 different players. And so we have that. Okay. And then once I have those theta values, okay, I'm going to generate values for the number of hits. Okay. And so here I'm going to just pick a random number for the number of at-bats, a random number between 100 and 400 at-bats for their actual data. And then we will generate how many hits they get, okay, based on the thetas that were generated, okay? And then I'm going to put them all together into this data frame here, okay? So here are my 8 players. So this player had 190 at-bats, 47 hits, okay? So if we estimated this player's batting average based on our observed data, it's going to be 47 divided by 190.247, okay? This is generated from a binomial distribution where the true value of theta is 0.2359, okay? So this player's true value of theta is this, but we can only get an estimate based on their hits, okay? And so some players, like this player actually has a pretty high true value of theta, but for whatever reason, their batting average when they performed wasn't so great, okay? They only got a batting average of 240, okay? So some players, their empirical data is higher than their true value, and some players, their empirical values are lower than their true values, okay? And some are, fairly close. So 0.247 is pretty close to 0.235, but this one's pretty low, 0.24 compared to 0.303. And then where's one where it's considerably higher? We don't have anyone. This is like the highest one, 0.26 compared to 0.245 or something like that. This one's probably like the most surprising one. But again, it's random, right? It's random, so we don't. Sometimes that happens, okay? Sometimes you flip a coin 100 times and you don't get 50 heads, you get only 40 heads, right? That happens sometimes, okay? And sometimes stuff like this happens too. But anyway, this is all we have. We only get to see the n, we only get to see the x, and based on that, we want to do inference about the true value of theta, and then we also want to do some inference about like the entire distribution for omega, considering all of the data that we've taken into account. Okay, so we're gonna use this software called STAN. There's been all kinds of different Markov chain Monte Carlo things. There was one of the earlier ones was called bugs, WinBugs, Bayesian something using Gibbs sampling was bugs. Okay, Bayesian inference using Gibbs sampling, and then there was JAGS, just another Gibbs sampler or something. And then STAN doesn't actually stand for anything. It was named after Stanislaw Ulam. This is Markov chain Monte Carlo. If you look up the history of MCMC, it actually originated back in where is it? Back in like during the Manhattan Project. Where is it? Metropolis algorithm. Yeah. Okay. Monte Carlo methods. Somewhere along the way, there's a history which says, okay. Yeah. So it's named after this man, Stanislaw Ulam, who was working on nuclear weapons during the Manhattan Project, and they were trying to do the math for, like, I don't know, nuclear reactions and stuff, and the math was too hard, and so they used this was they had these giant computers, but they decided to do random computer generation to kind of get an estimate, and that's kind of like the form. But everything was so secretive, so they needed code names for all of their projects, and so they chose Monte Carlo based on like Las Vegas gambling and randomness there. So anyway, that's what the namesake of this thing is. And it's you can learn about Stan's software for Bayesian data analysis, and it kind of has its own like language for describing the data parameters in the model and all sorts. There's lots of information, and if you go to getting started, they have information like how to get it installed and whether you want to do things. And so you can do it with Python. You can do it within R using RStan. That's what we're going to use. And so here's information on how to get it installed. There's lots of documentation and help there. But anyway, that's one of the tools that we can use. Okay. So there's 3 things you need to specify when you run things in Stan. You need to tell it about the data that's coming in. You need to tell it about the parameters that you want to get posterior distributions for. And then you need to tell the model, which relates how the parameters lead to the data. Okay. So as far as the data that's going into our model, we're going to tell it the number of players. We're going to just say there were 8 players. Okay. We're going to give it the data that we have, the X and the N inside our data blocks here. We're going to give it the X and the N there, which is the number of hits and at bats. Okay. We give it the hyper parameters for actually these are the hyper parent. Wait, now I'm confused. Okay, but yeah, so the ones, the arbitrarily selected ones. Okay, so omega, we're saying omega is a random variable, but we have arbitrarily selected the hyperparameters for omega, and then also k. All right, and then the parameters that we want to estimate, we want the posterior distribution for the different parameters. There's 9 of them. We have 1 for each batter, okay, a different theta. Okay, so we have a vector of thetas. We're going to have 8 values in this theta vector. And then we also have the overall omega, okay, for the overall thing, right? And we're trying to figure these out. We know what they are because we generated our data ourselves. So we know that the true omega is 25%, and we know that the actual true theta values are these, even though our data might not reflect the true values. Okay, so that makes things a little bit tricky. Okay, and then the model is like how did we get the data based on the parameters? So we're going to say, okay, this omega gets drawn from this beta distribution, and then we have to convert omega into an alpha and a beta, reparameterize. Once you have that, then you have your own beta distribution. That's going to generate the different theta values that you have. Okay. And then once you have your different theta values, then you get your x values from a binomial distribution. Okay, so that's basically the ideas we want to specify, and so we have to write this into our code. So the data block, so Stan has its own kind of language, I guess, for how you have to do things. So you have to declare things like this is an integer, and this is an array, and this is a you know, a real number, and so on and so forth. So I don't want to get caught up on all of the documentation stuff, but basically we're going to say these are all of the values coming in. Okay, so we have the value n. This is going to be 8, the number of players. We often specify lower and upper bounds, or at least lower bounds for a lot of these things. Okay. As far as our values go, x is the number of hits, and then n is the number of at-bats, the lowercase n here. And because we've got 8 of these things, we're going to say array square bracket n, okay, to say we've got 8 different values for x and 8 different values for n, okay? And then these are some arbitrary values that we select. In our case, k is 300, a omega and b omega are arbitrarily selected. I think we're going to, I want to say we specify 2 and 5 or something, just kind of, or maybe 2, I don't know. I forget what I specify in here. Okay. All right. What we need our values. We want posterior distributions. We want Stan or RStan to generate random values from the posterior distribution of omega and the random values for the posterior distribution of theta. Okay. Theta itself is a vector because we've got 8 different values here. Okay. So we're going to look at the random values drawn by Stan to just get a sense of these things. Okay. So omega is a real number between 0 and 1, and then and theta is going to be a vector of values there. Okay. All right. And then the model is, how is everything related? So we say omega is drawn from, and the tilde here means it's drawn from a beta distribution. Okay. And it's the shape parameters are a omega and b omega, which we specified is going to be values here. Okay. And then we need to transform from omega into alpha and beta. Okay, so I say we use omega is k minus 2 plus 1, omega times k minus 2 plus 1, and then beta is 1 minus omega times k minus 2 plus 1. Okay, I put an underscore here with the beta because beta is a reserved keyword described for the beta distribution, and here we want a beta value, okay, and that's a real number there. And then so anyway, once I have that, then I have a beta distribution with shape parameters alpha and beta that generates theta. And then we say, okay, using the binomial distribution and the different thetas we have, that's going to describe how we get our data values x, and n. That describes how we get our data values x. So this just shows how do we go from parameters that we need distributions for, posterior distributions, to get the data that we have. Because we have our data generation model says, you know, we kind of draw these things first. These things determine our data, okay? And with Bayesian inference and our Monte Carlo, we're saying, okay, but what I've observed is the data, and I want to do the inference back to the parameters up here, okay? And so we say, all right, this is how we go from, you know, that omega and that theta that we've drawn. Okay, so we go from omega to the theta basically via converting omega into alpha and beta. Okay, and then once we have the theta, we can generate our data values x there. Okay, and so this is all kind of described a little bit there, but basically this, we run that, okay? And then we have to run this in R. And so here, my I pass a list of values, okay, into, all right, I'm going to gather our different values into a list, and I'm going to call this stand data, all right? So I'm going to say, okay, how many rows do I have? N is going to be 8. I could just type these things in ourselves. I could say N is equal to 8. I'm going to take that column of X values to get basically a vector of the number of hits, a column of lowercase n for the number of at-bats, arbitrarily selected values of 2 and 5. So this is going to be like a, 2 plus 5 is 7, so it's going to be kind of really widely spaced. And then I think 2 plus 5, 2 divided by 2 plus 5, so 2 divided by 7 gives us around 0.28. So we have a mean of around 0.28, but it's like really diffuse, right? It's really kind of wide. And then, we arbitrarily selected 300, okay? All of the different kind of code blocks that we have here for the model and the parameters and all of that, that just goes into a big string, okay? So I have the data, the parameters, the model. This can go, you could also just create a text file and put the model in there. And so, you can also just create a text file called, whatever.stan or whatever, all right? And you can just put the model specification in there, but here we could just create a, a big long string here, okay? And then as far as running it, these are the two lines. You say one is you tell it to construct the Stan model. So when you install Stan and you use rstan, it's going to basically install like a separate program that has kind of this API to kind of send information to Stan. Stan, I think, is, I don't know what language Stan is written in, like maybe C++, I don't know, something for kind of performance and speed. And it basically sends stuff from R to Stan. Stan does its calculations and sampling, and then it sends the data back, okay? And it kind of gives you information about it. So anyway, we kind of initialize or compile the model by just saying stan_model, and we give it the model code. And here it's just this string, but again, you can specify a text file or something like that. And then once you have this model, which I store as object SM, here I'm going to say draw samples from it. And I say I want to use that model. The data that we're going to pass is going to be in this list where we pass to Stan, the N and the X and the N and the alpha omega and B omega and things like that. And then we get, and I say, hey, run 2,000 iterations, do 4 different chains, just in case the different chain, sometimes the chains get stuck, sometimes the chains go wildly off into different directions and stuff. All kinds of things can go wrong when you do Monte Carlo, Markov chain Monte Carlo. And then you can have a seed and so on and so forth. Okay, so here, this is just gibberish. Not gibberish, but this is just like the status of what it's doing, okay? And so, I don't know what it says. Gradient evaluation took that 1,000 transitions using 10 leapfrog steps per transition. I don't know what that's saying. Okay, adjust your, all right, so whatever. So it runs this. This is chain 1, and then it does it for chain 2, and then chain 3, and chain 4. All right, so anyway, all right, then it finishes, and then I say, okay, now give me what your estimates are for these different things, okay? And so it says, okay, based on all of the data I've seen, I now have a posterior distribution for omega, okay? That distribution has a mean of 0.25. Well, that's promising because that was our true value that we generated, okay? And it says, and you know, my 95% confidence interval, the 2.5 percentile is around 0.23. The 97.5 percentile is 0.28. So, you know, I'm like 95%. We have a 95% credibility interval going between 0.23 and 0.28, which sounds pretty good. Okay. And our 50th percentile is around 0.25, and so on and so forth. And we have that small, that's that. Okay. Our values for the different thetas. So player 1, our mean estimate for player 1's theta is 0.25. And we say, hey, you know, the values could be anywhere from 0.21, basically from the 2.5 to the 97.5 percentile, anywhere from 0.21 to 0.29, okay? Player 2 goes from 0.22 to 0.3. And, you know, basically, they're all kind of very similar, but, you know, some are shifted a little bit higher and a little bit lower, okay? So that's what we have here. It might be, what we can do is we can look at theta 1 and through theta 8 and compare that, okay? So again, yeah, our true omega value was 0.25. And then as far as we can say extract all of the values from the fit. So this gives us our posterior. And I could say, hey, what's the actual posterior value? And it's 0.2548. So this, you know, this truncated or rounded things off, but the 50th percentile, I guess, or the mean is 0.2548, and I don't know, there's a little bit of spread, but kind of close between the true value used to generate the data and the value we get from our posterior. I can just kind of take our columns and we can say, you know, the true theta were these different values. This is the value that was estimated, and this was our empirical batting average. And so remember, some players, their empirical batting average is lower or higher than what their true values are, and some it's lower. Okay, and so you know, everything kind of gets balanced out. This player's true value is 0.31, their empirical is 0.305, but kind of taking into account like all of the players' stuff, you know, it pushes it a little bit closer to the mean at 0.282. We had 353 observations. Okay, the ones that have fewer observations, their estimated theta is going to be closer to the kind of the group mean of 0.254. And then the ones that have more observations, theirs will be a little bit closer to their empirical batting average. Is basically what we get. Okay, you can also create a few plots. The trace plots here, this just looks like random noise here, but it's the different values that are being generated to form this distribution. So this is values from 1,000 to 2,000, and we see kind of like this hopping around, but it's showing that, you know, the values that it's generating are mostly between 0.225 and 0.30 with a, you know, strong concentration, at least for omega, between 0.25 and 0.275. Okay, and if we take the average of all of these different things that it gets for omega, it turns out the mean is really close to 0.254 or whatever it was, 0.255 basically. Okay. And then this is for player 1. And we can see the range on player 1 is a little bit, just a little bit different. So for the individual player, okay, there's a little bit, player 1's estimated theta is around 0.253. Player 2, I should have picked a different one whose estimated theta is like quite a bit different. Player 6 might have been more informative, okay? But it kind of shows just like the different values you get, right? You can also get, this is the same plot as this, just stretched, made a little bit wider, okay? And then this is the resulting density, all right? So you get the densities of the different things. This is the combo plot. okay, where we say I want the density and the trace, okay? Or you could just get the densities themselves, okay? And here we have the densities from the different, there's 4 different chains, and we can see all 4 chains, you know, have quite a bit of agreement among them, but that's what we have, okay? So these are the densities. Okay, that's how we run it. And again, I will just refer you to the Stan documentation as far as doing more models and stuff. Okay, we'll take I guess we'll take a step back and we'll just say like, okay, well, how does this kind of stuff work? How does Markov chain Monte Carlo even work? And we'll talk about Markov chains. But I think, is there a class called stochastic processes that's like 4.0 something? Yeah, I don't know. Okay. You don't see it? Okay. All right, maybe not. Okay. Well, we'll talk about this here. All right, but maybe you guys already talked about Markov chains, I guess, maybe a little bit. Okay. Well, sometimes you see the same stuff. Okay. All right. So as far as Markov chains, so there's all kinds of things. We're going to look at kind of a simple form. We're going to do discrete time, and I guess we'll start off with a discrete state, but you can also have continuous state and you can have continuous time. So, but we'll start off with discrete time. Okay. And so we're going to say, okay, where are we at time 1, time 2, time 3, so on and so forth. We call this a stochastic process. A stochastic process just means you have a sequence of random variables. Basically, you get one random variable, you'll get another random variable, and another random variable. Sometimes all of these random variables, like if you roll a die a whole bunch of times, that's a sequence of random variables, and it's a stochastic one. It's just not that interesting because every roll of the die is very independent of the others. Okay, the Markov chain, everything is not independent. Okay, but you have something called the Markov property, which says the next state depends on the one state before it. Okay, so you know, that's different from like I don't know, like a lot of games or whatever. The next state of the game depends on like what the entire history of the game up to that point. Okay, so you know what happens next, what's the next move, that depends on like the entire history. Okay, the Markov property says yes, the next move is not independent of the previous thing, but it only depends on the current state. Okay, so the next state depends only on the current state, not the entire history. So it's just you know, as you go from state x at time 1 to or time 0 to x at time 1 and x at time 2 and so on and so forth. Okay, so we'll say x at time n plus 1 rather than depending on everything from time 0 up to time n. Okay, it just depends on time n. Just what it is here determines the next one. Okay, not the entire thing. Okay, the state space is all of the possible values that the chain can take. And the Markov property means that the probability that the chain moves from state J moves to state J on the next step only depends on the current state I and not any of the other history. Okay. And so this means, yeah, so that's the Markov property. And then as far as this, we're going to just look at discrete state, discrete time Markov chains. We'll start there. Okay. So we write the state space if it's countable or if it's infinite, but these are all discrete here. Okay. We are going to define the transition probability as what is the probability that the Markov chain goes from state I, currently at time n, from state I to state J. Okay. So if we're currently at state I, what's the probability we go to state J? All right, and that is probability I sub j. That's what this probability is. So we were at probability with subscript ij is the probability of moving from state I to state j. Okay, if we're currently at I at time n, what is the probability we'll be at state j at time n plus 1? Okay, and so we gather all of these together and we arrange them into a big probability matrix. Okay, or this, sorry, this is our probability transition matrix. And so this says if we're currently at 0, what's the probability we go to 0? If we're currently at 0, what's the probability we go to 1? If we're currently at 0, what's the probability we go to 2? So on and so forth. This is if we're currently at 1, what's the probability we go back to 0? If we're currently at 1, what's the probability we go to 1 or stay at 1? If we're currently at 1, what's the probability we go to 2? Okay. All of these things, they're probabilities, so they have to all be between 0 and 1. Okay. They're all non-negative. And then the sum of the entire row, each row, the probabilities will add up to 1. Okay. Because this will define basically everywhere you can go if you start off at state 0. If you start off at state 0, you have to go somewhere. So the entire row adds up to 1. Okay, so each row adds up to 1 because if you start off at state I, you have to end up somewhere at the next time. And so so they all add up to 1. Okay, oh, that got really big. So here's a very, very, very simple two-state model. We have state 0 and state 1, and I've got arrows showing the different transition probabilities. Okay, so we could say, hey, 0 means we have sunny weather, and 1 means we have weather that's not sunny, so like cloudy, overcast, rain, or something. And we'll say if it's sunny today, the probability that it's going to be sunny tomorrow is 80%. Okay, and maybe it'll change and it'll become cloudy or rainy tomorrow with a probability 20%. Okay, and if it's cloudy or rainy today, the probability that it's cloudy or rainy tomorrow will be 40%, but maybe it'll transition and become sunny, and that's going to happen with probability 60%. Okay, so basically the arrows originating at 0 add up to 1. The arrows originating at 1 also add up to 1. Okay, and so our probability transition matrix looks like this. Going from 0 to back to 0 is 0.8, so that's this top corner, P00. Going from 0 to 1 is 0.2, all right, so that's P001. P10 is what's the probability of starting at 1 and going back to 0. And then P11 is 0.4, that's the probability of starting at 1 and ending up at 1, okay? And so anyway, this is all kind of listed out here. And yeah, we see each row adds up to 1. All the arrows coming out of a node add up to 1. So that's a very simple model. Okay, there's another model. This is the Ehrenfest-Ern model. If we wanted to set up a transition, this is a bunch of stuff here, but it can be used to simulate diffusion of molecules through a membrane. I don't know. So if you imagine like you've got, let me just jump to the picture that I have. Okay, so let's say we're going to just imagine this very diffuse thing, but basically we have, you know, 2 molecules over here and 2 molecules over here, and basically we're going to pick one of these molecules at random, and whatever molecule we pick, we're going to transfer it to the other side. Okay, the urn is basically, we can treat side A as one urn and side B as another urn. We have these different marbles and different urns. We're going to just pick one marble at random, take it out of whatever urn it's currently in, and move it into the other urn. Okay, so we have 4 possible molecules that we could select, or 4 possible balls that we could select. So if I select this top left one, okay, what happens? I take this and I move it over to here. So the resulting state looks like this. Okay, and so in that case, currently our X represents how many balls are in urn A, okay? Or how many molecules are on side A of the room, okay? So if I start off with 2, okay, there's a chance of ending up at 1, okay? So I went from 2 down to 1, okay? I could also select this molecule, and if I do that, I've gone from 2 down to 1, okay? But if I select this molecule, then it goes over into this side, and I will end up with 3 in A. And if I select this one, it will end up over here, and I will end up with 3 over here. And that's all of the possibilities that could happen, right? Because there's only 4 molecules or 4 balls, and so we have to pick one of them at random, all with equal probability. And so where do we end up? Okay, so out of the 4 possible transitions, 2 of them end up at 1, and 2 of them end up at 3. So therefore, my probability of going from 2 to 1 is 0.5, and the probability of going from 2 to 3 is 0.5, okay? And all other probabilities in that row will be 0, okay? If I start off at a different thing, so if I'm looking at row number 3, okay, if I have 3 molecules on side A and 1 molecule on side B or whatever it might be, okay, 3 balls and 1 over here, I could pick this one, and then if I move it to the other side, I ended up with 2. If I pick this one, I end up with 2. If I pick this one, I end up with 2. If I pick this one, which is also possible, I end up with 4 over here, okay? So out of the 4 different transitions, 3 of them, I end up ending up with a 2. One of them, I end up with a 4. So here, this represents how many I start off with. Starting with 3, I end up with 2 75% of the time. If I start with 3, I end up at 4 25% of the time. Okay, and so I could fill this out, and I can kind of follow the same logic for all of the other transition probabilities. Basically, we looked at row 2 and I guess the middle row and the the row after that. So the we calculated 2 1 and 2 3. Those are 1/2 each. Is 0 for everything else in that row, and then 3 2 is 0.75 or 3/4, and 3 4 is 0.25 or 1/4. 0 for everything else, and then you can also follow the same logic, and this will be your transition matrix. Okay, and this represents all of the transition matrices, the probabilities of the transition matrix here. Okay, and we can also represent it with this state diagram. And if we start off with 0 on side A, then 100% we will end up with 1 at the next state, okay, because 1 ball does have to come over. Okay, if I start at 1, 3/4 probability of going to 2, or 1/4 probability of going to 0. If I start at 2, 1/2 and 1/2, and so on and so forth, then I could represent this. And then if you want to generalize, then the Ehrenfest-Ern model will look like this, okay, with these different probabilities and so on and so forth. Okay, every Markov chain, well, not every Markov chain, okay, a lot of Markov chains will have a limiting distribution, and related to that, a stationary distribution. Okay, so we could say this is the probability distribution on some state space. Okay, and we'll say that pi is the limiting distribution of a Markov chain if if we let this chain run a really long time, okay, what's the overall probability of being in state J? Okay, that as n goes to infinity, what's the overall probability that we're at state 0, 1, 2, 3, or 4, or something like that? Okay, and so this is just given basically any starting position. Okay, so regardless of how you start, so whether at time 0 you're at whatever I, we just want to know what's the probability that you end up at J. Okay, and so if that limiting distribution exists, okay, it's the probability that x is going to be in state j, independent of the initial starting state. And basically, it's just like in the long run, what fraction of the time does the Markov chain spend in that particular state? Okay. And so if that limit does exist, what that means is that this Markov chain basically forgets its initial state and in the long run reaches some distribution according to pi. Okay. We say that distribution pi is a stationary distribution if when you take pi and you multiply it by the transition matrix P, okay, you get pi back. Meaning that if you're at this, if you start off with pi and then you let the Markov chain run and then none of the probabilities have changed overall, okay, the overall probabilities, nothing has changed, then we've reached a point of stationarity. Okay, it's kind of just like, you know, in the beginning, if you put I don't know, some incense in the corner of the room, okay, there's going to be a concentration in the corner, and you're more likely to smell it over in this corner than in the opposite side of the room, okay? But given enough time, that scent is going to kind of like disperse throughout the entire room, and eventually you'll reach this steady state where it's like equally spread out everywhere. There's this kind of this equilibrium, and you would have like equal concentration everywhere, you know, given enough time for this kind of thing to happen, okay? And so if the limiting distribution does exist, then it will be the stationary distribution, okay? This is basically, yeah, the stationary distribution is the distribution when it's at equilibrium. And there's this property called ergodicity or ergodic. So if we'll say if a Markov chain is ergodic, then that means it eventually converges to the stationary distribution, okay? And the idea of a Markov chain being ergodic or ergodic, I don't know how to pronounce this, okay, is basically you can start at any state. Like if I take that incense or that candle and I put it in this corner of the room or that corner of the room or some other corner of the room, granted that it's like concentrated enough and I seal up the room and we don't have like the air conditioner or some air filter going or something, okay? It doesn't matter which corner I put it in, eventually it should diffuse throughout the entire room, okay? So we could start the chain at any state, and at some arbitrary time in the future, t, okay, then the probability of being in any of the other states has to be greater than 0, okay? And this has to be true for all t greater than some finite value here. So we don't want to just say for at infinity. We just want to say at some arbitrary time t in the future, okay? And we won't get into like super formal definitions of theory and things here, but there's two properties. We're going to say the Markov chain has to be irreducible and aperiodic, okay? Irreducible just means all of the states communicate with each other, okay? If it's not irreducible, it's reducible, okay? And basically, all that just means is that if you start off somewhere, anywhere you start, you can eventually get to, there's a path that exists to every other state, okay? So wherever you start. So if I start off at 0, there is a path that gets me to 4. I might have to go through a bunch of other states, but there is a way for me to get to 4. And if I start off at 4, there's a way to get for me to get to 1 or 2 or 3 or 0. Basically, all of the states communicate with each other. So this one is irreducible, okay? This is an example of something that is reducible. This is not irreducible because here, there is no path. If I start off at 0, there's no path for me to get to 3 or 4, okay, right? If I start off at 0, I can only go to 1 or 2 or back to 0. I can't get to 3 or 4, all right? And so this is reducible because the reason why we call it reducible is because if I start off at 0, 1, or 2, I can reduce my diagram and just throw away states 3 and 4. I don't need to, there's no reason to include this if I start off at 0, 1, or 2. Okay? All right. And then, so that's the idea of, we said it has to be irreducible and it has to be aperiodic. Okay? So irreducible is that idea, all the states communicate to each other. Okay? A period is the greatest common divisor of the number of steps you can take to end up back at itself. Okay? So if we start off at 3, I ask, can I get back to 3? And if so, how many steps will it take for me to get back to 3? Okay? So I can get back to 3 in 2 states. I can go from 3 to 2, back to 3. That took me 2 steps. Okay? I can take 4 steps to get back to 3. All right? I can go 3 to 4, back to 3, to 2, back to 3. All right? That's fine that I stopped at 3 in the middle. Okay? I can also go 3 to 2 to 1 to 2 to 3. That takes me 4 steps. I can go 3 to 2 to 1 to 0, back to 1 to 2 to 3. Takes me 6 steps, so on and so forth. And we'll find that to get back to state 3, it has to be an even number. Okay? There's no, I can't get back to state 3 in 1 or 3 or 5. If I said you need to take 3 steps, okay, there's no way to end up back at 3 if I tell you must take 3, an odd number of steps. Okay, so this has a period of 2. Okay, and so some things have a period of 2. Okay, if I add one more thing where I say from 4 we can end up back at 4. Okay, now we can say, all right, how many steps does it take to get back to 3? Okay, I can get back to 3 in 2 steps. I can go from 3 to 4, back to 3. Okay, I can also, if I say, hey, I need you to get back to state 3 in 3 steps, I can do it. I go to 4, I go back to 4, and then I go back to 3. Okay, and I could take 5. If I say, hey, I need you to do 5 steps, I go 3, and then I can just go 4, 4, 4, 4, and or however, whatever I need to count, right? I can just kind of abuse state 4 until I get the right count, right? So in this case, if we look at how many steps, the greatest common divisor here is just going to be 1. Okay, state 3 has a period of 1, and so a Markov chain is aperiodic if all of the states have a period of 1. Okay, and then if a Markov chain is irreducible and at least one state is able to go back to itself, the chain will be aperiodic. All right, and if it's irreducible and aperiodic, then it's going to be ergodic. Okay, and then and if it's ergodic, it means it will eventually converge to a stationary distribution. All right, so that's like the theorem. We're not going to prove any of this mathematically or anything, but this is just kind of the idea, is that if you have this chain and it's all of the states communicate and it's aperiodic, then it'll eventually converge to a stationary distribution. Okay, so we had this Markov chain, we had this probability transition matrix. This is the very simple 2-state Markov chain. We either start off at state 0 or state 1, and we can go from 0 to 0, 0 to 1, 1 to 0, 1 to 1. I don't know what happened to the picture there, but it looks like that. Okay. Now, what we want to do is we want to figure out, okay, what's the stationary distribution of this thing? Okay, what's the stationary distribution? Where if I have some distribution over 0 and 1, like if I start off with a 50% probability of in 0 and a 50% probability in 1, does that mean at the next state I will also be 50% probability 0 and 1? In that case, I won't be. But we can try to figure this out, right? And we can say, okay, if we start off at state 0, we can kind of say okay, how much is going from 1 to 0 and how much is going from 0 to 1. We want equilibrium. Basically, we want the amount flowing in this direction to be the amount flowing from over here to here. And if kind of the amount flowing in opposite directions is the same, then we've reached equilibrium, okay? So we can say if we start off at state 0, the probability of going to state 1 is basically this arrow, 0.2, okay? So that's the transition probability, 0, 1. And basically, the amount flowing from 0 to 1 is going to be how much starts off at 0. So that's going to be P0 times that probability of flowing, of transitioning to 1. So that's going to be P0 times little p0 times transition probability P01. So that's basically like how much is going in this direction. Okay. And similarly, we do something over here where if we start off at 1, there's a 60% probability of going over to 0, and the amount that's going to be flowing is going to be basically the probability of starting off at state 1 times that probability of 0.6. And so what we want is at the stationary distribution, we want to figure out the value of pi 0 and pi 1 so that 0.2 times pi 0 is equal to 0.6 times pi 1. Okay. And then, and this is just a little bit of algebra. We know that the stationary distribution has to add up to 1 because if there's only 2 states, 0 and 1, those two things, those probabilities have to add up to 1. All right, and so with a little algebra, we get pi 0 is 0.75 and pi 1 is 0.25. And indeed, if I do 0.75 times 0.25 times this transition probability matrix, okay, we will see basically 0.75 times 0.2 gives me 0.15. And then if I have 0.25 times 0.6, that also gives me 0.15. So I have 0.15 going this way and 0.15 going that way, all right? If I start off with 0.25, then 0.25 times 0.4, 0.1 goes back. So the amount kind of flowing into 1 is 0.15 is flowing in, and 0.1 is flowing back to itself. So we remain steady at 0.25, okay? Similarly, 0.75. So basically, so if I do 0.75 times how much flows back to itself, 0.8, how much is flowing in from state 1, 60% of state 1, so 0.6 times 0.15, we stay steady at 0.75. And then over here, for how much is flowing into state 2, 20% of the stuff coming from state 0, so 20% of 0.75 flows in, so 15% flows in. And then 40% of the stuff that started off at state 1, so 0.4 times 0.25, 0.1, also 0.25. So anyway, I started off at 0.75, 0.25. After applying the transition probability matrix, I end up back at 0.75, 0.25. So that is our stationary distribution. If once we reach 0.75, 0.25, that's equilibrium. The transition matrix, it stays at 0.75 to 0.25. Okay, so here I did algebra to figure this out. This, we can also figure this out using eigenvectors, okay? So it feels a little bit awkward, but this is a vector times a matrix, and it's equal to the same vector, right? And so that's kind of in the form of an eigenvector. Normally, eigenvectors, we see matrix times a vector is equal to scalar times a vector. And here we have vector times a matrix is equal to basically vector times 1 or scalar times a vector. And so this is an eigenvector. It's just called the right-hand eigenvector, where we normally, this is the left-hand eigenvector. We're normally accustomed to seeing the right-hand eigenvector where the vector is on the right-hand side of the matrix. But here we have the vector on the left-hand side of the matrix, and so this is the left-hand eigenvector. The left-hand eigenvector is just the transpose of the right eigenvector. Just a little bit of math to kind of show that. So if I take my transition probability matrix and I find eigen or I use eigen in R to get the transition, the eigenvectors. Eigen gives me right eigenvectors. So basically, I'll just take the right eigenvector and get the transpose of it. I'm sorry, the left eigenvector is equal to the transpose of the right eigenvector of P transpose. Okay, sorry. So basically, I take P, I transpose P, I get the eigenvectors of that thing, and then I transpose those back. Okay, so anyway, if I do this, this is my eigenvector, my first eigenvector here. I transpose that. Okay, and the default settings in R is that the sum of squares add up to 1. So if I do 0.948 squared plus 0.316 squared, it adds up to 1. But I don't actually want that. I just want to kind of scale these down. And so these are still in the ratio of 3 to 1. Okay, this is 3 times bigger than that. And so that gives me, if I just divide by the sum of that column, I get 0.75 and 0.25. So I get the same values here. Okay. So indeed, the stationary distribution is 0.75, 0.25. We've demonstrated that it's also the left-hand eigenvector of the transition probability matrix. And we can simulate a Markov chain, okay? And so in this Markov chain, we're going to say, all right, start off at some initial state, randomly, wherever you are, look at your transition probability, and then randomly select a state there. And so we just say, hey, do this 10,000 times. Okay. So we say, draw a value between 0 and 1. Okay. Whatever that is, look at what row you're in. Okay. And then use that to draw your probabilities of going from 0 to 1. Okay. And so this will run a Markov chain. We'll get a whole bunch of zeros and ones. And we can say, okay, after 10,000 iterations, how often were we in state 0? And it was just under 75% of the time. How often was I in state 1? About 25% of the time, just a little bit off. Okay. I could say, what if I started off at state 1? Okay, so here I started at state 0. What if I started at state 1? Okay, same kind of thing. I end up around 75% of the time in state 0, around 25% of this time in state 1. Okay. There's also a nice little visualization that kind of shows this eigenvectors and all of this. The idea here. So this is a two-state transition matrix, or two-state thing, and the thickness of the arrows is kind of like the transition probability. And here it's just like we have people moving from California to New York and people moving from New York to California. Okay, and so I think I can kind of try to get this. What were the numbers I used? 0.8, 0.8, and 0.6. Okay. So we're going to say 80%. If you start off in state 0, 80% remain in state 0. So let's see if I can get this. Oh, it's really hard. 0.79. Okay, I think 0.79 is the closest I can get to 80%. Okay, and then over here we want to say 40%. So if we start off at state 1, 40% probability of remaining in state 1. So I'm going to shrink that down to, yeah, I had it. Okay, 0.39, I think. All right, and we can start with like different amounts. I can start off with a tiny number, and like I think the max over here is 38. I can also shrink it down to something. Okay, so I'm going to do something like this. Okay, and so this is kind of like our transition matrix. And if I hover over this, we see this represents the diagram, and what we see is what do we have? 20% of this circle goes over here, and then 60% of this circle goes over here, okay? And so when I start here, I can even just, I could have everything, I could have my both circles equal size, and what we're going to see is 20% of blue goes to yellow, and 60% of yellow goes to blue. And it's going to reach a steady state when you have a 3-to-1 ratio. Basically 75% are in blue and 25% are in yellow, okay? So I start off with basically exactly blue and yellow exact same size. 20% of blue is going to go to yellow. 60% of yellow goes to blue, okay? 20% of blue goes to yellow. And now I think we've reached equilibrium where the amount flowing from over here is the same amount flowing from over here. And that's, here we have this is basically 4 times bigger. Or I'm sorry, 3 times bigger, 75%, 25%. You know, we could start with basically nothing in blue. 20% of blue goes to yellow, 60% of yellow goes to blue. And yeah, now we've reached equilibrium here where the amount is flowing that way, okay? And I can kind of do it this way. Everything starts off in blue. 20% of blue goes to yellow. 60% of yellow goes to blue. And, you know, we reach equilibrium where the amount kind of goes there. So that's a nice little visualization there. Okay. All right. What else do we have here? Okay, so we have oh, we got a lot of stuff. Okay. I'm going to just keep powering through. Okay, so we have the Metropolis algorithm. Do I want to talk about all of this? Yeah, I do. Okay, let me just see what we have, because yeah, I do want to talk about all of this. Okay, it's not too bad. All right, we'll talk about the Metropolis, and then we'll go to the Gibbs sampler. And then we'll do a little fun demo here. Okay, so, let me give you second answer is D. D as in dog is our second answer. You know what? I'll just go ahead and give you your third answer before I forget. Third answer is E. E as in elephant. Okay, D as in dog, E as in elephant. For answers number 2 and 3. Okay, so when we do Markov chain Monte Carlo, the goal is to design a Markov chain so that the stationary distribution of the Markov chain is the desired distribution that we want to generate samples from. Okay, so to kind of backtrack, you know, when we talked about all the way back here, when we're talking about the baseball example, okay, the baseball example, we have this posterior distribution that is this, where did it go? It's this complicated thing with a bunch of stuff, right? It's this, the posterior distribution is, you know, the distribution of theta 1, theta 2, up to theta n and omega. This is the distribution that we want. This thing is hard, okay? But we're going to try to generate samples from this, okay? So this is the distribution that we want. We want this thing to be proportional to whatever this thing multiplies out to be, a binomial times a beta times a different beta with a hyperprior and all of this. This is the thing that we want, but we're like, how do we generate values from this? Okay, it feels hard. So what we're going to do is we're going to try to design a Markov chain so that the stationary distribution of that Markov chain is that weird, complicated distribution. Okay, and that feels like, that sounds crazy, right? Like, how are we supposed to get Like, I didn't even know how to design a Markov chain in the first place. And you're telling me we want to design a Markov chain so that it looks like this crazy distribution that I don't know how to describe, okay? And so, so this is what we do. We say we have some target distribution that we want, P, okay? And we might not actually know, we might not even know the final form of P, okay? So remember that complex distribution way back here, we actually don't have the actual distribution for it. All I know is that it's proportional to this thing, okay? I just know it's proportional to this. I don't know what the normalizing constant is. If you told me to write down the formula for this, I might be able to write this stuff down. Like there is a defined thing for the binomial and a defined thing for the beta and a defined thing for this beta. And I can kind of try to write it all out, but I don't have the normalizing constant. So I don't actually have the thing. I only have something that's proportional to it. But with the Metropolis algorithm, that's okay. Okay? I only need something that's proportional. Okay? We only need an f of x that's proportional to that target distribution that we want. Okay? And then we have the way we're going to design our Markov chain so that it ends up sampling from this target distribution is we need a way to kind of propose values to use. Okay, so we have a proposal distribution. There's the Metropolis algorithm. There's the Metropolis Hastings algorithm. Metropolis says your proposal distribution needs to be symmetric. Okay, and basically the proposal distribution is if I'm start at one spot, I need to be able to propose another value. And so it could be as simple as like, if I start at state 1, I'm going to flip a coin. And if it goes heads, I'll propose the state to my right, 3. And if I get tails, I'll propose the state to my left of 1 or something like that. Okay. Or if it's like a continuous thing, I can say, all right, I'm going to, if I start off at 2, okay, if I'm currently at the value 2, I'm going to just draw a random normal value, which is sometimes positive, sometimes negative, and I'm going to just add that to 2, and that's going to be my proposed value. So maybe I draw a random normal value, and I randomly select the number 1.1, and I add that to 2, and I say, now I'm going to propose the value 3.1, okay? Or maybe I draw a random normal value, and I get negative 0.5. And I say, okay, well, now I will propose the value 1.5, whatever, right? So we just have some way to propose new values given my current state. And so I say, given the current state, draw a candidate. This is going to be my proposed value from this proposal distribution, whether it's flipping a coin, drawing a normal random value, you know, some other thing. I propose I have a proposed location. All right. And then I calculate something called the acceptance ratio. Okay. If the value, the probability, or my function that's proportional to the probability, if the probability at the proposed location is more likely than my current location, okay? So if I do f of x proposed and I compare that to f of x that I'm currently at x at time t, if it's greater than this thing ends up being 1, I'm going to go there for sure, right? So if I'm on a normal distribution or whatever, and I propose this other location, that place is more likely and the target than my current value, I'm going to go there for sure. Okay. If it's less likely in the target distribution, right? I look at my function f, which is proportional to my target distribution. If it's less likely than where I'm currently at, I don't say I'm not going to go there. I say maybe I'll go there, depending on how likely or unlikely it is compared to my location. Okay, so I take the ratio between the probability of the proposed location and the probability of my current location. So let's say at the target distribution, the proposed location is 1/10 as likely as my current location. I will go there with probability 1/10. Okay, if the proposed location is like 80% as likely as my current location, then I go there with probability 80%. Okay, so I go there in proportion to how likely that place is compared to my current place, okay? So, and then do I go there or not? So if I say, oh, I have a 10% chance of going there, I generate a random number between 0 and 1. If it's under 10%, then I go, and if it's greater than 10%, I don't go, okay? If I say there's an 80% chance of going there, I generate a number between 0 and 1. If it's below 80%, I go. If it's above 80%, I don't go. So if U is less than that, I accept it. Otherwise, I reject it, okay? If I don't go there, I reuse the current value that I have, okay? And if you set up your Markov chain following these steps, that Markov chain is ergodic, and eventually, given enough samples, the samples you generate following this chain follow the desired target distribution P. It feels like magic a little bit, but it ends up working, okay? And again, you only need a function that's proportional. You don't need the actual function. And I talk about this, but basically the thing comes down to this probability of moving. And if you just have something that's proportional to it, it's basically P times a constant. Those constants just cancel out. So it's equivalent to just using that proposed value. And this is super helpful in Bayesian statistics because we often don't know the marginal probability, which is a normalizing constant. We only know the numerator. And so we often just use the numerator part, okay, which is simple enough, okay? As far as the proposal distribution, it could be anything. One suggestion, again, is just selecting a random normal value centered at your current location, x at time t, okay? But you can also pick a uniform value centered at x at time t, where you're going to generate values between x at time t minus c and x at time t plus c. And so if you're currently at 2, maybe you generate random values between 1 and 3 or something like that, okay? So this is just a silly example, but I say, hey, let's say we wanted to generate our target distribution is a normal distribution centered at 15 with a standard deviation of 3, okay? The PDF of this distribution is this, right? If you plug in mu equal to 15 and standard deviation 3, we have that. I can ignore the normalizing constant, and I can just say, hey, f of x is proportional to our target PDF, which is e to the negative 1/2 of x minus 15. Is something going on? I don't know. Okay. X minus 15 over 3. I guess I gave the last few quiz answers. All right. So what was I saying? All right. Okay. So we're gonna just generate. I'm gonna propose values centered at my current location, plus or minus 3. So I'm gonna, if I'm currently at 2, I'll generate a random value between -1 and +5. And I'm gonna say, hey, do I want that value? Yes or no? Okay. And just to show you how this works, okay? Remember, the target distribution is a normal distribution centered at 15 with a standard deviation of 3. So, 95% are within 2 standard deviations. So 2 standard deviations being around 6. So 95% of our values will be between 9 and 21, okay? And 99.7 will be between 6 and 24. I'm going to start at a terrible location of 100, okay? There's no way 100 is going to be part of my final, like, this normal distribution would never generate a value of 100, okay? But I don't know that, all right? I'm going to just say, hey, eventually I want my Markov chain to generate values from this target distribution. But I don't know where to start. I don't really know what my target distribution looks like at the end of the day. I'm going to just start off at this terrible location of 100, okay? But what I'm going to say is, given your current value, just pick one random uniform value between current -3 and current +3, okay? And then we're going to evaluate the function using this thing that's proportional to it, e to the negative 1/2, e of negative 1/2 of x minus 15 over 3 squared, okay? So this is proportional to the target PDF. Okay, so I start off at 100. And then what I do is I say, okay, that's my current location. Let's propose a value at my current location. So I propose a value somewhere between 97 and 103. Maybe I propose 98. Okay, so let's say I propose 98. I look at f of 98 versus f of 100. And when I do this, I get, oh, because it's a negative value here, right? 98 minus 15 squared versus 100 minus 15 squared. This is going to, 98 times negative is less negative than 100 minus 15 squared. So basically, the proposed location, f of the candidate, is going to be larger than f of my current, okay? And so this p move is going to be a value bigger than 1. I generate a random number between 0 and 1. In that case, it's for sure going to be less than p move. So I'm going to accept the proposed candidate, okay? And so the candidate is going to become my x at time t plus 1, okay? If I rejected it, so like, again, if I started at 100, maybe I can propose any value between 97 and 103. Maybe I propose 102, 102.5, okay? If I propose that, the candidate location is less likely than my current location. So I'm going to, I generate a random value, and I'm probably not going to accept it, okay? If I'm currently at 100, and let's say my proposed location is 100.01, okay? 100.01 is the f at the candidate location is probably very similar to f at the current location. So I might get like a value of like 98%. And so I'll accept it, very likely. And so I'll just move just a tiny bit up, okay? So anyway, I either accept or reject it, and then I do that. Okay, so anyway, I run this. So I start off at 100, and what we can see is that I just, like in the beginning, you know, I move down. I don't know what this value is. I propose something, I move down. It looks like around, I don't know, 60, 80, I'm like 90, around 90, I probably kept proposing positive numbers, like 93, 92, 92.5 or something, and I kept rejecting them. So I kept reusing that same value. And then I started proposing smaller values, like 80 something, 80 something. And so it just keeps going down, 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 and eventually, remember, our target, it has a mean of 15, standard deviation of 3. So we want most of our values between like 9 and 21. Okay? And so when we get to around 20, 21, now we start to bounce around. Okay? And we start proposing values that are higher, proposing values that are lower. Sometimes I accept the higher ones. Sometimes I don't. Sometimes I accept lower ones. Sometimes I don't. And I get this chain, this Markov chain that says, okay, given our current value, let's propose a new location, and we get a bunch of things, okay? All of this stuff, this is junk, okay? Because I had a terrible location, and the beginning part, it takes a long time to kind of reach where I want to be, okay? So this is what we call the burn-in period, and I'm going to just throw these away, okay? So I throw those away. I discard the first 180 values or so that burn in, okay? And then I just say, hey, let's look at the values that I kept. And let's look at it, all right? And this is the distribution of the values that I kept, which seems like it fits our target distribution pretty well, where we have a mean of 15 and a standard deviation of 3, okay? I can look at my empirical CDF, which we get a pretty good match, and so on, okay? Your proposal distribution plays a role in the efficiency of your Metropolis algorithm. So if you propose something where it's just proposing like crazy values, like every single value is going to get rejected, right? If you say, you know, if you're currently at 2 and you say, hey, let's propose anything plus or minus 100, okay? So you're proposing like positive 102 or negative 96 or something like that. It's going to say, no, I don't want that. I don't want that. I don't want any of these values. And so you end up getting this kind of, oh, okay. So this is independently IID values drawn from the target distribution. Like this is like the ideal scenario. Like Markov chains will never get IID because by definition, Markov chains are not independent. Okay, they're always dependent on the previous value. So you're never going to get true IID. But this is like the dream scenario to get something close to IID. Here, I think, yeah. So if I look at my entire chain, it's not perfect. Okay, it's not quite IID, but it's not terrible either. And we can see most of the values are, around 15 plus, give or take a few. I have a few things where I'm going to say, all right, let's propose something plus or minus 100. Let's propose things plus or minus 1. Let's propose things plus or minus 12. Okay, with 100, okay, with a width of 100, I'm going to say take my current value, I'm sorry, plus or minus 50, I guess. And I run the algorithm. My trace plot looks like this. Okay, this is a bad sign. All right, what we see is a lot of kind of flat areas. When you see a whole lot of flat stuff, it means it got stuck at a certain location because every time it rejects a value, it reuses the same value. So basically, I was like at 15, I kept proposing, plus or minus 50, up to plus or minus 50. So I might have proposed like negative 30. I might have proposed 60. And it says, yeah, we're not going to take 60 because that would never happen in this normal distribution. I'm not going to take negative 30. That's not going to happen either. So I get stuck at here. And then finally I proposed like 12. And I said, okay, I'll take 12. And then, so we get kind of this, almost looks like a skyscraper skyline or something where we have all of these flat lines here. Okay. If your proposal distribution, your proposal distribution has too small of a width, okay, then it's like you're going to accept every single value, right? If I start off at 15 and I say, oh, I propose at 15.1, okay, 15.1 is hardly any different from 15. What's the probability at 15.1 versus the probability at 15? They're going to be very similar. So you're going to accept it with like a 90% probability, even if it's slightly less probable. Okay, so you're going to accept almost every single thing that you're proposing. And so you kind of take this random walk and you just kind of end up everywhere. And eventually, everything is ergodic. So it's just like you have to let it run for a long time. Even this one with a terrible proposal distribution, if you let it run long enough, it will look like the stationary distribution. But you got to let it run a really long time. And same thing here. You let it run long enough, it'll get it right. It just takes a long time. Okay. Here, you play around with it, plus or minus 6 with a 12. And this is the trace path, which, as far as like comparing it to the IID situation back here, like this seems to be the one that's like coming the closest. Okay. So yeah, that's what we like. Okay. And then, all right. And then the last one is the Gibbs sampler. So the Gibbs sampler technically is a special case of the Metropolis algorithm, but it's probably better not to think of it that way. It's especially helpful when you have like these hierarchical models, because the Gibbs sampler is, you might have this high dimensional posterior distribution where you have a whole bunch of different parameters all together. And you can factor it out into a whole bunch of conditional distributions, okay? And so you can get each parameter's conditional distribution given the other parameters, okay? And then you draw a random sample for each of those parameters one at a time. And so if you have, like, we had 8 baseball players, and we had a theta 1 and a theta 2 and a theta. We had a theta for each baseball player. We're going to say, all right, what is the conditional distribution of player 1's theta given all of the other values? Okay, and in that case, actually, player 1's theta only depended on the omega and doesn't actually depend on the other player's theta value. So it ends up kind of factoring out in this fairly nice way. Okay, but we would generate random values for theta 1. Once we get a theta 1, we generate a value for theta 2, then we generate a value for theta 3, and we do that so on and so forth. And you generate one value at a time in kind of this cyclic fashion. and that completes one iteration, and you do it again and again and again, and eventually you get a whole bunch of values from this high dimensional setting here. Okay. All right. I just kind of want to. we'll end the lecture notes here, but I wanted to show you this little demo where I think it's kind of fun of using Markov chain Monte Carlo for trying to like solve a puzzle. Okay. All right. So, okay, here it is. All right. So this is actually based off like a real. There's like a real problem that happened in real life. So anyway, I guess there was like a prison, and then the inmates in the prison were sending messages to each other, and the prison guards were worried that they were planning something bad. Okay, but whenever they intercepted the messages were ciphered. Okay, and so they couldn't understand what it was that they intercepted, and so they wanted some help to try to decipher these things. Okay, this is very different from encryption. So in this case, ciphering is just a very simple, what we call a substitution cipher. It's like what you did as a kid when you were pretending to be a spy. You know, it's basically like every time you see the letter A, replace it with an H. Every time you see a B, replace it with a T. Oh, this is notes from a different class, right? So I said on Monday, but just forget that part. Okay, but so anyway, you just kind of replace this, and so let's say this was the message we had intercepted. Okay, and we say, well, okay, how do we translate this, or how do we decipher this? Okay, all right. One possibility is like, okay, maybe you pick up like another scrap of paper that says this is the cipher key, and you go, oh, okay, I found the thing. But then you apply it and you say, okay, I have a Z. Z means the original letter was K, and then I have a T, and so T means the original letter was a B, and you go through this thing, Z, T, R, Z, Y becomes K, B, D, K, E, and you apply this, and this is supposedly the deciphered text. And you go, oh no, this doesn't seem correct. Okay, this piece of paper that has the cipher key, this can't be the right cipher key, right? And so you can say, okay, well, maybe I have to try another cipher key. But there's like potentially 26 factorial cipher keys out there, which is like a huge number, and there's no way for us to really be able to brute force this. Okay, there's a lot of strategies you could use. Okay, but what we can do is we can try to evaluate. We can compare one cipher key with another cipher key, and we can try to compare the likelihood, or I guess the posterior probability of one cipher key versus another cipher key. Okay. And so, if you find another scrap of paper that says like, oh, this is a different cipher key, okay, you can kind of compare these things, right? So, and these all look, so here they're 26 factorials, like on the order of 10 to the 26, right? And let's say you find these three different cipher keys, and it says, okay, H turns into A, and U turns into A, or X turns into A. And if you apply all of these things, they all just seem like total gibberish, right? You apply this one, you get KBDKE. You apply this one, you get GKNGV. You apply this one, you get KFPKM. Okay? So it feels hopeless because every single one of these things is bad. Right? And just kind of proposing one random cipher key and hoping it's a good hit, that's not going to work. Okay, but maybe what we can do is we can kind of incrementally improve one. okay, at a time. And so we're going to use the Metropolis algorithm, and we're going to say, okay, I know this cipher key that I started off with, it's terrible, okay? But even though it's terrible, what if I propose another cipher key that's almost exactly the same, but I'm going to just make one change. I'm going to just take two letters and swap them. Okay. So here's the first cipher key. A goes to H, B goes to T, C goes to N. This one is exactly the same, but the only thing is I'm going to take this letter. I'm going to say over here, G and B are aligned and O and E are aligned. And over here, I'm going to swap them, and we're going to swap B and E. And so it becomes G gets aligned with E and O gets aligned with B, right? And so what happens is that this word, RB, okay, gets over here, the R corresponds to D and the B corresponds to G. So when we translate RB, it gets translated or ciphered into D, deciphered into DG. And over here, the R is still D, but this B goes to O, okay? And so instead of DG, we get DO, okay? And so over here, we have BGD, and over here I have BOD. And over here, I have, I don't know, we have a few things where we have, words like DO appears and stuff. And so even though this gibberish, this is complete gibberish, and this one's complete gibberish, this one feels a little bit better than this one. As far as like, are we moving towards getting something that's not going to be complete gibberish? This one feels a little bit less complete gibberish than this one. Okay, so we'd say that's an improvement, right? And so we'll take it. Okay, and so how do we evaluate whether it's like super gibberish or less gibberish? Okay, rather than just going off of like our gut feeling and saying like this because I see BOD here versus BGD here, like this sequence of letters feels a little bit better. Okay, we are going to take two parts. All right, one is we're going to just look at letter combinations. Are certain, if we see certain letter combinations, we're going to say that looks like combinations we see in English. And if we see other letter combinations, we're going to say that doesn't seem like combinations we see in English, right? So if you see T and H next to each other, like that's, I think, probably the most common two-letter combination in English, just because the word the shows up so many places. So you see TH a lot together. So that's a good thing. But if you see like when we tried our first thing, we see KB and we go, how many words have a KB next to each other? I don't think that many, right? How many words have a B and a D next to each other, or how many words have a D and a K next to each other? Like, not that many words, maybe some words, okay? And other, like, letter combinations, a Q followed by an F, that doesn't seem like it happens organically in English very often. So we're going to give low probability scores to these things. We're going to figure this out. Oh, I'm going to run out of time. Okay. All right. And so we assign a value to basically every two-letter transition probability. We go, 26 letters. We go A through Z. How likely are we to see A followed by A followed by B, A followed by C, and so on and so forth. Okay. And then so we'll take that into account. We'll also take into account, like, if as we're doing this, if we find any real words, we'll do that. Okay. And so anyway, we do this thing. We apply our function to calculate the likelihood of this versus the likelihood of this. We don't know the final probability distribution, but we just need something proportional to the likelihood, okay? Because the remember, the total posterior distribution is proportional to the likelihood times the prior. The prior is like the distribution, the prior distribution across all possible letter factorings or letter mappings. And so we're just going to leave that as a constant because there's no reason to believe one letter mapping is more likely than that. So we're just going to say the final probability is going to be proportional to the likelihood, and then we're going to just evaluate the likelihood at the proposed letter mapping versus the current letter mapping. And so we'll run that, and so this is my cipher code, and so this is our coded text, and let me see if I can make this a little bit bigger for you guys to see. All right, so it starts off with this thing, and then I can just say like, all right, if this is one possible mapping, how does it translate? Okay, it translates into this gibberish, KBDKE. That's not helpful. That doesn't feel useful at all. Okay, to get my two-letter transition probability matrix, and you can run this code because I posted it on Brew and Learn. Right, as you can download this. I have like the full text of the English translation of War and Peace, and we're going to scan through it basically 2 letters at a time. It takes a couple minutes to run, so I'm going to just skip over that. I've saved the transition probability matrix, and I'm going to load it up here, and I can create a plot of this. And so this is the transition probability matrix of if your first letter is A, what's the probability it gets followed by A? So A is frequently, so darker spots means it's frequently followed by that letter. So it's A is frequently followed by an N, okay? It's also frequently followed by R, S, and T. That makes sense, okay? Here we have, if you start off with an H is followed frequently by an A. H is very frequently followed by an E, also frequently followed by an I, also frequently followed by an O, pretty much the vowels, okay? Non-vowels that is followed by is, it looks like it's followed by T and R and U, I don't know, okay? N is frequently followed by A, C, D, N is followed by D a lot, N is followed by G a lot. So if you look at like what does G follow a lot? Like this column is pretty blank, but then we do have a spot at G, okay? And then we have O followed frequently by F because of the word of and things like that, that being a very common word. If you look at Q doesn't show very frequently, so its entire row is very light, and there is just one spot that's just barely visible, and it's Q followed by U, but pretty much Q followed by every other letter is like almost never happens. And then what's followed by Q, almost very few. Like this entire column is almost close to blank. Similarly, J, this entire column. So anyway, this is actually what like the iPhone keyboard. It's okay. All right, I don't have time to get into that. But this was like a big thing. All right. So anyway, and then there's another thing where I have a lexical database, okay, which basically just says like what's the probability of this one word showing up, right? And so if it sees the word the, it gives it a high probability. And then and so anyway, we're gonna run this loop where it's gonna run the Metropolis algorithm. And it's going to start off again with a total junk potential translation, okay? But then it's going to say, all right, what if I propose a swap, and if it's a little bit better, like if we go from BGD to BOD, we say, okay, BOD seems more likely than BGD as a combination of letters as far as English goes. We will take it. And so we just incrementally improve, right? Rather than just trying to propose a random, something that's totally random, and then just hoping we happen to hit it, we're gonna, so we'll run this loop. And so basically in this loop, I say, hey, propose a swap, calculate the probability of the proposed swap versus the current one, and if it's better, take it. All right. And so so we'll go ahead and run it. and so it's running now, and so it started off. This was the first proposed thing. It's total junk, but as it's going on, so we see like there's no way that's a real word, right? But then as we go on, it just proposes swaps so that instead of getting NGGNDHZB, now we have HAB, which feels better as a combination. Okay, and eventually, now we have IFFIR, and then IMM and AMMAL, and so now this is still total gibberish, but it feels a little bit more like something that could be some language, not English yet, okay? But then we start to see English words, okay? So again, we started off with total like IZWIE, VYJAIN, or JAIW, VYJ, okay? And then after around 70 of these things, we have ERTEN, HADUET, and then now we have had to be on rot to be that, okay? And so that starts to feel like, okay, there's something there, okay? Now we have had duet, had to be, do we have, and eventually, all right, it's 8:50, but if you stick around, we'll get there. Okay. Do we have a sense of what this could be? All right, it says Ayrton had duet had to be on rot to be that s the siest por weven TPS robuen. So there is a weighting that says, okay, this is how much we want to see these words versus like this is how important the two-letter transitions are. And so there's kind of like a knob that you can kind of turn a little bit. I'm a little nervous that like this is not going to work, but it will. I think I tested it out. It worked earlier, but again, so we're using the Metropolis algorithm to say this is my current cipher key. It's not great, okay, but it's better than the one I had before. And can we try proposing a letter swap? And so maybe some letter swaps I propose and I say, okay, what does it look like after we swap those letters? And it says, oh, that looks even worse, so we don't accept it, right? And then others I propose and I say, oh, that looks a little bit better, so we take it, okay? And then we try another letter swap and we propose it, okay? All right, we have enter hey set hey to PE or not to PE. That is the question. Whether 'tis Notker in the mind to sullar the skings and arrows, ol outrageous Lorton, or to take arms against a sea old troopsies. Okay. Oh, here we go. Enter Hamlet. Ham to, okay, to pee or not to pee. That is that is the question, whether 'tis Knockler in the mind to suffer the slings and arrows of outrageous fortune, or to we want to see take arms against a sea of troubles, and by opposing end them. Okay. All right. I want the P to become a B, so at least we get to be or not to be. But it's just doing random, right? At this point, we could probably be like, all right, let's just like human intelligence will do better than the random. Do we got it? Oh yes. All right. So Hamlet to be or not to be. So okay. Now we have questions spelled with a C. Okay. But we have it mostly right. Whether 'tis nobler in the mind to suffer the slings and arrows. What? Yeah. Phonetically, yeah. Oh, it just the letter Q it hates, right? Like it's not gonna really like the letter K. Oh, we keep getting something similar. Question with a K. Back to question with a J. Um, I think at this point it's just like we're just hoping it hits the Q by randomness, right? But here, we got pretty good, I think. Hamlet to be or not to be? That's the question, whether 'tis noble, right? So this is Hamlet. All right, and so it's supposed to be to take arms against the sea of troubles and by opposing end them. All right, well, I'll just call it a day here. I think that's. Oh, we got it, the Q. All right, now we just need the V and the K to switch by random chance. But yeah, I'll just stop it here. So we got almost there, but we have that. Okay. Anyway, that's it. So thanks for sticking around, you guys.